So next we will move on to the next speaker, Praveen Ravirathinam. Welcome.
Yeah. Hi everyone. My name is Praveen and I am a PhD student under Dr. Vipin Kumar. Today I'll be talking about our recent efforts in trying to build a multimodal knowledge guided foundation model for spatio-temporal remote sensing applications. It actually ties into a lot of concepts that were talked about in the previous two talks. So we'll be trying to address some of them and try to show our progress in some of the aspects that were discussed. So to start out, let's just talk about what do we think about as the environment as a system. So if we were to think about the entire environment as a system, we would envision it as the physical drivers such as temperature and precipitation act upon a region which contains certain characteristics such as the land cover type or the soil characteristics and the management practices, which would lead to some response, which could be crop growth or stream flow or some emissions of some sort, which are observed by these satellites or sensor data that are present throughout the world. So this is the broad perspective of the environment. And now I'm going to talk about the ideas that we want to bring into our foundation model. So if you think about most of the foundation models being built right now, including NASA IBM's Prithvi model, the Stanford SatMe, Ringmo, and Satlas, all of them use only the satellite imagery when building their foundation models. But the downstream tasks that they are trying to solve are the system characteristics or response related characteristics. That's what they're trying to solve in their downstream task. And like it was mentioned in previous talks, that they're only using satellite imagery to do this, which may not have a direct relationship with the downstream tasks that they're trying to do. So that is but all of these things that they're trying to solve have direct relationship with the physical drivers that drive these things. So that's our first idea. Our first idea is to use multiple modalities of data in both the pre-training and the downstream tasks. In specific, in this work, we show how we want to use weather as well as the satellite imagery together to build a foundation model, which will then be fine-tuned for downstream tasks. Now, another thing which was mentioned in previous talks was the pre-training task that we need to choose. The most common pre-training task used by everyone in the remote sensing domain has been masked auto-encoded, which is you hide part of the image and you try to reconstruct the entire image. But if we are trying to include multiple modes of data, this pre-training task would not actually capture the relationship between these two modes in this pre-training task. So we want to choose a pre-training task that would be able to capture the relationship between the physical drivers and the satellite data together in the pre-training itself, so that the embeddings that are created by this foundation model would already contain this information, which would then be fine-tuned for downstream tasks. So to that, we need to go beyond reconstruction. We can't use reconstruction as a task for that. So what we propose is using forecasting as a pre-training task. So what do I mean by that is, if you have a satellite image right now and you give it the weather till a future date, and then you ask it to predict the weather, the image in that future time, it would be possible for the model to learn how the satellite imagery responds to the weather data it's provided, and it thus creates an image in the future. So creating this as a pre-training task forces the model to learn the relationship between the weather and the satellite imagery. So these are the two ideas that we are basing our study on. And just to provide some architecture details, this is our general outline of our architecture, is that we have an input series, an encoder decoder fashion, to get an output series. So what our model does is it uses multiple modes of data, that is I2, which is it uses I2, which is multiple modalities of data, that is satellite and weather data. And our pre-training task is variable step forecasting. That is, we are trying to predict a future image which can be of any length. So we range it from up to 10 days or 200 days. So effectively what we're trying to say is, we give you a series of images and we tell you, give me an image 20 days in the future or 50 days in the future. And we give you the weather till that point, because otherwise without the weather, it would be very difficult to figure out that image. So the most commonly used task, the most commonly used setting by almost everyone else is I1 and T1. That is, they use a single modality of data, the satellite imagery, and they try to do masked autoencode. So we have names for these, which might get a little confusing, but the acronyms are something like MMVSF stands for multimodality variable step forecasting. SMAE is single modality masked autoencoder. The other methodology that we would first be comparing with is where we use the single modality and we try to do variable step forecasting. That is, you just give it a satellite image and then you try to say in the future, just tell me what the satellite image is without, just give me the number of days without giving you the weather, what's happening in the future. So that would be one baseline, and opposed with our baseline where we give the weather as well. So these are three examples to highlight the benefit of our methodology. So in the first row, we can see that our input are these 6 images, and we are asking it to predict an image 120 days in the future. And that's given by the ground truth image here. So there are two main things to note. One is that within those 120 days, you can see that this particular patch has greened up, as in some growth has happened. And you can see that this particular field has been harvested. And you can see that in our methodology, the one that uses weather, you can see that both of these have been captured. There is the green up as well as the harvesting has happened. But in the methodology that uses only satellite imagery to do forecasting, you can see the green up doesn't happen, and even the harvest doesn't happen very clearly. It's still a little green patchy. So this shows that the embeddings created by our weather model are able to capture land growth characteristics within its embedding. And it also shows that since the inclusion of weather has helped in identifying these land cover characteristics. Now, the second example further highlights that the impact of weather. So you have 6 images, and you're asking to predict an image 90 days in the future. And you can see that within those 90 days, snow has happened. And you can see that our model, because it has weather information, it has added snow, whereas without the weather information, there is no snow present. And another thing to note is that it has not added snow uniformly everywhere to the entire image. It has added snow only mainly in the parts that are identified as fields. So that shows that the model is not only capturing the information with weather, it's also identifying a little bit of terrain characteristics as well, which is further demonstrated by the third example, which is we have an input of 6 images in a mountainous region, and we're asking it to predict an image 200 days into the future. And you can see that 200 days into the future, there's not much of a change because mountainous regions don't change much unless there's snow or something. And you can see that our weather model keeps the image more or less the same. But you can see that without weather, you can see that there's false green up happening. So this shows that there is terrain information that's being captured, land growth being captured, as well as the relationship with weather being captured. So this model shows that the embeddings go beyond simple temporal autocorrelation, which could help potentially in the downstream task that the model would be fine-tuned on. So to show one example of a downstream task, we chose to do crop mapping, which was highlighted in a previous talk. And we compared this against the embeddings that were created in the most standard setting, that is using the single modality and using masked auto reconstruction. And we see that the model was trained using 2018's data and was tested in 2019. And we can see that there's almost a 10% increase because of the inclusion of our methodology. And with this, I'd like to conclude and just say that it's better to use these kind of multimodal approaches in our framework and also design a pre-training task that helps in the downstream task. Thank you.
Thank you very much.
Thank you. That was, for me, particularly timely because we're ramping up remote sensing analysis of lake images and trying to combine remote sensing with in situ models, essentially to do a similar thing. So what other modalities in the case of predicting crops could you imagine? And you've got satellites, you've got weather forecasts,
Yeah.
What else?
So we are thinking about using soil moisture soon, soil moisture and soil characteristics inside as well. But as of now, we are still discussing with other agriculture people as well, like what else modalities could we use. Right now, we have the weather data itself has so many bands that we don't know which bands are useful. We've chosen according to what we think are some bands. So we're still expanding on that. And with regard to water, though, we could, because of the fact that we're using precipitation and other things, one of the downstream tasks we thought of was flood forecasting. So if, for example, if you have a series of images, you have a lake and it rains a lot, it will fill up, which is flood forecasting. So it would do better than the standard imagery. That was one idea we had.
That was wonderful. If you could go back a couple of slides, I thought this was almost magical what you did. So you had 6 images. There you go. And the weather at those time instants as well.
We have the weather till the day of the prediction.
And So that's weather from minus infinite to that day, or weather?
So we have it from the first day till the, so for
the
example,
6th day.
no, so these are not one day apart. They could, so for example, if this is on the first day, like day one of the year, and this is on day 30 of the year, let's say, and this image is 120 days in the future, so it's totally 150. So we have the weather data for those 150 days.
So the weather data is not for exactly those 6 time intervals or 6 time instants.
Yeah, it's for the throughout. Yeah, it's continuous. We have one weather reading per day.
So I'm fascinated that somehow you find out that it's actually going to snow when it has never snowed over the entire duration of those 6 training sets.
There would have been snow so in this example, we are asking it to predict 90 days in the future. So we are giving it the weather for the next 90 days.
Okay. I get it. I thought you were only giving it weather for the same time that you were giving it image data as well.
No. So we give weather till that day.
All right. I was thinking you're doing magic.
Yeah.
Thank you.
But can you train the model, like say, like using the data from the previous years and learn the seasonal patterns?
Yeah. Right now we're using only 2020's data, 21's data only, and we're globally sampling it across the world. But we want to refine it to a further thing.
Gotcha.
Here we go. I was wondering with the single modality images on the far right, they seem very pixelated.
Yeah.
What's going on there?
Okay, so we trained both of these to the same extent, and we were also a little surprised by this. The theory, the hypothesis we have is that you're trying to map X to Y, and I don't think there's a proper solution to that unless you give it Z, and Z being the weather here. So without X and Z, it's not able to arrive at a proper solution, because it might, for example, without weather, these two images, like the first two examples, they seem very similar. Like they just look like 2 crop fields, and you can see that one of them's ground truth has snow in it, but the other one is still like very barren. The only way that for us to differentiate between those two would be with the information of weather. Without weather, it may be just guessing, which is why this one is still like a little green.
And I don't know if you follow causality, but if you had like a structural causal model,
right,
for all of these things, that would basically tell you what you needed to sample to generate your subsequent images, right?
Right. Yes. So
so do you have an SCM for something like this?
So our architecture is a little causal in nature, in the sense that we don't do any back propagation or anything. It's just only a forward-based approach. So we have those concepts inside our architecture, but not explicitly like you mentioned.
All right, let's thank Praveen again for this great talk.